Morning.
Good morning, yeah.
Mike,
Yes, dear.
I have to run real quick and pick my son up. He just threw up on the bus. So,
No problem.
all right, I'll be back.
No problem. Sure, no problem, dear. Hey, guys. Now, before I start, does anybody have any questions?
No.
Okay, so you guys good on the flows?
Yeah.
Okay. That sounds good. Okay, guys, so I guess that's okay. The next topic that we'll talk about is going to be energy gradient. And what energy gradient mainly is meaning is we can say, okay, moving from areas of high energy to low energy. Is that clear? Okay, and that's pretty much okay as what we will say is okay. Well, in this case, it's okay. Keep the blood flowing. Okay, that mainly is okay. Will move from an area of high energy to an area with low energy. So that motion from high to low energy is called the energy gradient. Did you guys get that?
Yep.
Good. Now, without doubt, there's no doubt that, okay, yes, let's do it this way, that the major form of energy that ensures the blood moving from high to low energy gradients is the energy of pressure. Yeah, okay, which we mainly is okay, if you guys remember yesterday, especially is okay when we talked pulsatile flow. Okay, now what was it that the heart did when it contracted? Okay, the walls of that contracting chamber actually is okay, put a pressure on the blood. So here's okay, what's going to happen? The pressure is going to increase. Okay, where okay in the blood vessels, we can say we had a relatively low pressure. Okay, so due to this increasing pressure in the heart, in the chambers of the heart, that pretty much caused that the blood move from an area of low pressure, or from an area of high pressure to an area of low pressure. Okay. Primarily, the major reason for that is going to be pressure energy. Did you guys get that?
Yeah.
Right, okay. And of course, now since we can say now due to that the pressure will be greater here, but then we will have a lower pressure here. And it's just going to move from here to here. Mainly it's because more and more blood is being pumped by the heart. But generally speaking, that motion of energy from from areas of high energy concentration to areas of low energy concentration is what we call an energy gradient. Any questions about that?
No.
Okay. That we mainly said, yes, pressure energy is not the only one, but the major form of energy that is going to ensure that movement of blood. Okay, this is actually causing the blood to be moving from, you can say from the heart to the blood vessels. And it's from the blood, within the blood vessels, it's from area of lower pressure or greater pressure to lower pressure, greater pressure to lower pressure, greater pressure. And that's how it keeps on flowing and flowing and flowing around. Did you guys get that?
Yep.
Good. Now, as we just said, now pressure. Well, so let's put it this way here. Okay. Energies, we can say, responsible for, let's say, blood flow. And the reason that we use the word flow, because blood is a liquid. So that motion of blood, a movement of blood is going to be referred to as blood flow. Okay. Now the three major forms of energies that is going to be responsible for that is primarily going to be pressure energy. There's going to be another form of energy that we will call kinetic energy. And one that we just going to mentioned by name. Not really go into a whole lot of details about is going to be gravitational energy. Okay. But these are the three major forms of energy that mainly will be responsible for the blood flow from heart through vessels and from vessels back to heart. Is that clear?
Yes.
Good. Any questions?
No.
Good. Now, guys, one thing that, yes, we will come across, but it's, if you look at it, it is mainly just an action of repeat or action repeat, if you want to put it that way. And that's as we can see, the law of conservation of energy. Okay. And what is that going to mean? Or what is that going to be? That will mean is okay, we'll say it's okay, the total energy. Total energy is going to be equal to the sum of special energy the kinetic energy and yes, okay, the gravitational energy. At any point, whether we say it's okay, the total energy here, we can say it's okay, point A, the total energy here, which we'll find called point B, the total energy here is going to be, what's the C? At all points, the total energy is going to be the same. So, okay, but what is it they're going to be made up of? The sum of your pressure energy, your kinetic energy, and gravitational energy. Is that clear? So the sums of these energies here are going to be the same at any point within the blood vessel as a result of this, okay, law of conservation of energy. Okay, now later on, yes, okay, what we mainly, yes, okay, will be doing is mainly, yes, okay, just primarily, yes, okay, just focusing on these two energies here. Okay, so what we previously, yes, okay, called, yes, okay, the law of conservation of energy, which may say that, okay, its total energy at any point is going to remain the same. But when we, yes, okay, take the relationship using these, considering these two energies here, we're going to talk about something that we call, yes, okay, the Bernoulli's principle. Clear? Okay. Which mainly because says, okay, that he mainly is okay, mainly study as okay the relationship between pressure and kinetic energy. So either as okay, this may be greater or lower, this may be greater or lower, but at any point, the sum of these two energies here is still going to be the same, whether it's point A, point B, point C, and if you go D, E, F, and so on, so on. Okay. So, but what we can say is that, okay, it's throughout the blood vessel. Whether that blood vessel narrows, whether that blood vessel expands, exactly. The total amount of the energies, which is going to be as okay, the sum of these three energies is always going to add up to be the same. So if for instance says, okay, that here the value was 20, it is going to be 20 here, it's going to be 20 here, it's going to be 20 here. Okay. That may be as okay ups in your pressure energy, which mainly will cause that, okay, yes, you will have downs in the kinetic energy, or vice versa. If there is this, okay, was ups in the kinetic energy, that will mainly mean that, okay, yes, we will have downs in the pressure energy. But when we add them up, they're going to be adding up to the same. Did you guys get that?
Yeah.
Yeah. Okay. Now, guys, the first form of energy that I would like to talk about is going to be pressure energy. Okay. Now, what was energy? Mainly as something which has the potential ability to do work, or as lead to work. What did we call what is work? Okay, applying a force and moving an object. In physics, that's what we call work. Pressure energy is going to be as energy which is due to pressure. What was pressure?
Is it force over area?
Force over area, right? Okay. Clear? Okay. Force over area. So if we had an area and as we apply a certain force on that area, that force over that area is going to be as what we'll call pressure. Okay. What this force actually is going to be as the energy that is going to be transferred over to an area. Clear? Okay. Now, guys, pressure energy as per nature is a form of energy that we call it is a potential energy. Okay. Now, what we mean by potential energy is mainly as an energy which can be as stored, or we can say as a stored form of energy. Is that clear?
Yep.
Okay. Now, first of all, yes, we look in the circulation. Yes, where is it that this pressure initially is being produced? We said that earlier, in the heart. Okay, pretty much yes, by the contraction of those walls of the chamber. What is it that we will do? It will mainly is put a greater force onto the blood, okay, in that chamber. That increase of force, okay, is going to be as that there will be an increase in area or increase in pressure, okay, where you say that pressure just becomes more and more and more as the heart chamber squeezes more and more. So what we actually had was an increase in the pressure, which mainly caused that blood is going to be pushed into the blood vessels. In this case, that's the arteries. Okay, and that volume of blood is being pushed from the chamber of the heart into the artery is mainly as going to cause that artery is going to expand, and that's what we feel as a pulse. Yeah, okay. Before, yes, that blood was pushed in, yes, what this artery here would have been offering was some sort of resistance. So it's pretty much yes, when this pressure in the heart is okay increases to an extent that it'll be able to just okay push the blood with enough pressure to actually just okay overcome this resistance of the artery here to let the blood flow. Okay, that's where we says okay that the pressure in the arteries in the heart is now greater than okay as the pressure of the resistance offered by the artery. So that's when it makes yes okay this became a higher pressure and this now was a lower pressure. Okay, when this heart here is okay, for instance, okay, dilates. Now, how does it dilate? Mainly because that the pressure falls in the chamber. Clear? Okay. But what mainly is okay prevents the blood from flowing back from the artery into the chamber is mainly as okay those valves that close behind it. Okay, and that mainly causes okay as then it's okay here just flows okay from higher pressure to lower pressure along the blood vessel. Okay, but now it's okay that's going to be it's okay there was a pressure that was built up in let's say it's okay the atria. Okay, but here's okay the pressure is greater than in the ventricles and plus now the ventricles even increase in area. So when they increase in area, that's going to cause us, okay, a decrease in the pressure in this chamber here. And that's how it's okay now. Here you have a greater pressure, here you have a lower pressure. It's mainly as okay due to that pressure difference that okay as the valves open and now let the blood flow from atria to the ventricles. From higher pressure to lower pressure. Did you guys get that?
Yeah.
Any questions?
No.
Okay. So please keep in mind, guys, pressure energy is a form of, it's a type of potential energy. And why do we call it potential energy? Mainly because that it is a stored form of energy. Okay, now what was pressure? It was mainly as okay, that's the concentration of force on area. Here is okay, you can say that the force is mainly as okay going through as okay in the case of the circulatory system. It's going to either be as okay applied by the walls of the heart, or as or the walls of your vessels. Okay, but it's mainly as okay a tug of war between as okay greater pressure versus lower pressure that ensures that okay blood mainly as okay will flow from areas of high pressure to areas of low pressure. And even as okay within the vessel from higher pressure to lower pressure, from higher pressure to lower pressure. And of course, that's okay, more and more pressure is going to be applied because that's okay, newer it's okay, bulks, if you want to put it that way, of blood is going to just okay be pumped from the heart into the blood vessel with every contraction. Did you guys get that? Okay, so an increase in the pressure initially it's okay, comes from contraction of the heart. Okay. Where, okay, yes, that's going to be as okay, a fall in the pressure in the heart. Okay. Due to relaxation. Any questions? Any questions?
No.
Okay, guys. Now, the next energy that we may be talking about will be kinetic energy. Now, guys, energy was energy. But if you look at the word kinetic, it was pertaining to tick and the kind. Meant motion. Yeah, okay. So we can mainly say that, okay, as any object that is in motion, or any substance that is in motion, can only be in motion if it possesses or has what you can call kinetic energy. If it lacks kinetic energy, it's okay, it will be at a standstill. It will not be moving. Is that clear? Okay. So if you, for instance, okay, see a ball on the field, there's a ball, whatever ball you call it. Okay, now right now, yes, okay, here it is, because it's okay, not moving because it is lying still. Did that make sense? Now, you may see that, okay, as somebody comes and kicks this ball here. Okay. Now, the eye of a layman will say, okay, somebody kicked the ball. The eye of a physicist mainly will see that there's going to be a transfer of energy from that moving foot to the ball. And now due to that, just okay, this ball here is okay, now will have kinetic energy. And will be as okay, either rolling down the ground or that's okay, go up in the air. Did you guys get that?
Yep.
Okay. So the word kinetic energy or the word kinetic itself is pretty much self-explanatory. It's going to be the energy pertaining to, or that's okay, pretty much okay, responsible for the movement of any object. Anything that you see moving is because it has kinetic energy. Did you guys get that? Now, guys, the main way to, yes, okay, calculate kinetic energy is mainly going to, yes, okay, be mass times velocity. Yeah, okay. That is going to make us, okay, calculate or determine the amount of energy that may be, for instance, okay, needed to, yes, okay, make an object moving. Did you guys get that?
Yes.
Okay, so that's what I said. That's okay. That ball here, because that's okay, football or soccer ball, when it was at rest or not moving. Although, yes, okay, it had a mass of, let's say, yes, okay, sorry, 10 pounds, for instance. Okay, but since it was not moving, there was no velocity, no speed, no motion. And the amount of kinetic energy that it had was also equal to 0. Because anything multiplied by 0 is equal to 0. Did you guys get that? Now, if we say that, okay, yes, you want this ball here is okay to move at a certain speed, let's say it's okay, for instance, okay, 1 meter per second. And let's say it's okay, it weighed 10 kgs, for instance. Okay, the main is okay, then just says okay that you might have to, yes, okay, use this, okay, that's okay, use this much kinetic energy, joules, whatsoever that they call it. Okay, but if it was a lighter object, let's say it's okay, just 1 kg, and you still want to, yes, okay, move it at the same speed, you might just need, okay, yes, because it's okay, 1 kilojoule or something like that. Okay, did you guys get that? So this kinetic energy here pretty much is going to be, yes, okay, what we will range, yes, okay, look at, is going to be directly proportional to the velocity. Above the velocity, mean, yes, okay, just speed. Okay, so something which has more kinetic energy, if we, for instance, okay, keep the mass constant, will have a greater velocity or be flowing at a greater speed. Whereas if it was a lesser kinetic energy, yes, okay, that mainly mean that, okay, it flows at a lower velocity or at a lower speed. Right, okay. If you, for instance, said, okay, this light ball here, 1 kg. Okay, and that's why I say, okay, people may see as, okay, somebody kicking the ball. Now, yes, okay, there can be two ways of kicking the ball. Yes, okay, that can be a slide kick. Clear, okay. So that slide kick is maybe, yes, okay, going to be lesser kinetic energy transfer over to the ball. And for instance, okay, it may, yes, okay, just run at a, or yes, okay, move at a slower speed. Whereas, okay, if somebody is okay, come like this, dumb, and then kick the ball, that's mainly going to be as okay that they are going to end up transferring more kinetic energy over to that ball. And okay, yes, since its mass is constant, but it's okay, that greater kinetic energy transferred, it may that's okay going to cause that it may that's okay move with a greater speed. As a result of okay, the greater kinetic energy is okay transferred over to it. Did you guys get that?
Yeah.
Yeah, okay. So just think of okay as rolling a pen on the table versus just okay a big rock. Clear? Okay. Now you can say, okay, that rock may be round as well. Okay. But it's okay, since that pen is lighter than okay as a big rock, it will yes, okay. It will require lesser kinetic energy. Clear? Okay. To move. Okay, now if you apply the same amount of energy to the rock and the pen, of course, that's okay. The pen will be moving faster than the rock. Two objects with the same mass, if same energy is applied, well, okay, they will move at the same speed. Whereas, okay, yes, objects with the same mass, but greater force and lesser force, or greater energy and lesser energy is applied to both of them, or to each of them. The one with to which is okay, greater amount of kinetic energy is going to be transferred is going to be moving faster versus the one to which is okay, lesser kinetic energy is transferred. Right. Any questions? And what man just had learned, not man, okay, but had learned is okay, or is okay, observation was that okay, as a round thing moves easier or faster. And that's just okay how they thought of okay as inventing the wheel, which was round, rather than having yes, okay, a square tire. Just think if your car had square tires, it would take more energy to just okay make that tire make one full rotation. Just okay, driving from here is okay, just down the block would consume maybe it's okay 10 times more gas than you use now because it's okay, the tires are round. Yeah, okay. But kinetic energy is mainly as okay, where we later on will mainly as okay, just translate into that's going to be responsible for the velocity. So greater kinetic energy mainly will mean higher speed or higher velocity, as we'll call it, or lower kinetic energy is going to be as okay, what we'll call lesser speed or lesser velocity. Is that clear? Yes, students.
Yes.
Yeah.
Okay. Or you can say it's okay. So the faster you run your car, yes, okay, you're using more kinetic energy, or it's using more kinetic energy, which comes from fuel. So you end up burning more gas. Okay. Okay, guys. Gravitational energy, now something that we just mainly as okay, just going to mention by name, and not going to just okay a whole lot of details about it. Primarily because okay, when it comes down to just okay the final discussion of the energy gradients and so on. So what we mainly as okay will be more focused on is going to be as okay the pressure energy being added up with that's okay the kinetic energy. Whereas some of these at all points is going to be the same. Yeah, okay. So gravitational energy. Now, just like pressure energy is also, yes, okay, it's a form of potential energy. Now, what did we mean by potential energy? Stored and, okay, yes, able to perform work. Or we can say that it has the potency to perform work. Okay. Now this is mainly as okay going to yes okay be related to yes okay because that's okay elevation of objects. Now for instance, okay, we have an object here at this point. We can just say it's okay point A. Let's say it's okay, this is a ball that you're holding in your hand. Clear? Okay. And what you mainly as okay do is you throw that ball up in the air. To this point here, which is going to be point B. Okay, now what the ball actually is okay will be doing as it is elevating or flying up in the air, it actually is okay is going to is okay increase in gravitational energy. Okay, and that's pretty much okay going to be the energy that mainly is okay at some point is going to just okay elevate to a level that's high enough to cause it to come back. Clear? Okay, so the higher an object is going to be, that's okay, the greater is going to be the gravitational energy. We can say it's okay at this level, yes, okay, here it was 0. Here it might be, yes, okay. Or this level here is okay because it's okay, it was 10. And as it comes down, it's going to be 9, 8, 5, 7, 6, tick, 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 back to 0. Did you guys get that?
Yep.
Okay. Now, do you guys know what gravity is? Yes, guys.
Yes.
Do you mind tell us what gravity is? Or is that a secret that you want to keep with yourself?
It is a force that is that like 9.8 meters per second or something.
Okay, good, 9.8 meters per second. And what does this 9.8 meters per second do?
Keeps us on the ground.
Okay, it keeps us in the ground. Okay, but that's actually, that's okay, that it pulls us with this force. Okay, of course, that's okay, it has a limitation. Okay, so that's okay. If you're strong enough to just okay throw this ball here out of okay, yes, the range of the pull of gravity is okay. We know it's floating in the wide in the space. Maybe it's okay ending up as okay landing on the moon or Mars or so. Okay. But guys, okay, don't worry that much about it's okay gravitation energy. Just remember this much. Just like your pressure energy is a potential energy. What do you mean by potential energy? It's a stored energy. Okay. And it's going to be as okay, mainly as okay, be determined by the elevation of objects. Okay, where we mainly will say that okay, as objects at a higher level is going to have greater gravitational energy. Okay. But guys, when we come down to yes, okay, talk about yes, okay, the sum of the energies, we will end up being yes, okay, just be focusing at these two here. Any questions? Okay. So sum of the energies at any point is going to be the same. Okay, which was okay due to this okay law of conservation of energy. Okay, then we say it's okay now. Two things is mentioned in this law here is okay that the energy can't be produced or not destroyed. Okay. but can change its form. Okay. Now what we may say here is, okay, this destroyed here is okay. We can also say, okay, maybe it's okay, loss. Clear? Okay. Now, what we will do in just a little bit is that we'll talk about as okay energy losses in the circulation. But this loss is actually as okay not loss, but it's made as okay just that energy that the blood carried that may as okay just change its form. So it's actually not loss, but it's just some of that energy that the blood carried in form of kinetic energy, pressure energy, etc., that changes its form. Okay, so the value of okay is your kinetic energy, your pressure energy, is okay, will get lower practically, but it's not a loss, but it means it's because some of that energy is okay is converted into other forms of energy that we may as okay just say okay, that energy that the blood carried initially as okay is lost, which is wrong because it just changes into another form. Yeah. Okay. So guys, just read on your okay energy gradients, and when we come back, we'll talk about okay the losses of energy. And okay, maybe we can even just okay then talk about okay stenosis. So I see you guys at 10:15. Okay, guys. Okay, guys. So we're going to talk about okay loss, which is not really loss, but we can okay just say it's okay change of energy forms. Okay. During circulation. And circulation, I mean, it's okay, just that going around and round and round and round of blood. Okay. So we can mainly say it's okay that there will be, we talk about it's okay, 3 forms of loss of energy. First is what's going to be it's okay, viscous loss. Second is going to be it's okay, what we will call frictional loss. And the last but not the least is going to be it's okay, inertial loss. Now, guys, before talking about yes, okay, viscous loss, let's just talk about it like what does it mean to be viscous. And now we can mainly say as okay, viscous or viscosity, as we may call it, is going to be as okay the thickness of a fluid. Yeah, okay. Where you can say as okay, a fluid which is thicker fluid And if I says, okay, I may have a fluid which is thinner. Fluid. This thicker fluid is going to be referred to as or have a greater viscosity compared to as okay, the fluid which is thinner is going to have a lesser viscosity. Clear? Did that make sense?
Yep.
Good. Now you might have heard the saying that, okay, yes, blood intake is thicker than water, right? Have any of you heard that?
Yeah.
Good. What does that mean? What does it mean when somebody says blood is thicker than water?
Usually when somebody says that has to do with relationships and family.
Okay. So family bonds are stronger. Okay. Or family is family, if you want to put it that way, right? Okay. But if you look at water compares, okay, side by side with blood, you'll find that, okay, yes, physically, yes, okay, the characteristics of blood is thicker than that of water. Or we can say, okay, that blood is going to have a greater viscosity than water. Clear? Okay. Or likewise, yes, okay, honey. Honey is going to be thicker than water. Do you guys know how to test real honey? Just because a label says raw honey doesn't mean that it's real honey.
Isn't it if you add water to it, it depends on how much like the waves in it?
So you will actually have to dilute the honey to check whether it's real.
Yeah.
Okay, then whatever is real honey, you just spoil a lot of good honey.
Don't use a lot of it. You don't need a lot.
Nah, that's not real.
Yes, it is. It absolutely is.
I don't know how you test honey. But real honey, my dear, is, have you ever seen those, I don't know what to call them? But if the honey is able to just, okay, run, and the thinner the string it forms without breaking, means that it is pure. Okay. And usually it's okay, darker honey is more pure than lighter honey. But, okay. But, clear, okay. Now what is going to be as okay? Okay. Viscous blood. So you made it so okay, blood that is going to be more viscous or more thick. It's going to have, okay, it's going to be more viscous. Clear? Okay. Did that make sense? Now just think of it, guys. You have a straw. Well, we can say, okay, and later on we will just say, okay, that this straw here is okay, will be, okay, a blood vessel. You have a straw. Clear? Okay. Or let's say it's okay, you have two similar straws. Now, in one straw, yes, okay, we're going to, yes, okay, push a fluid with a great viscosity, or which is going to be thick. Where, okay, yes, through the other straw, we're going to, yes, okay, transfer fluid which has a lower viscosity, or which we can say as okay, will be thin. Is that clear? Okay. Now, as far as okay, as what we will call as okay, viscous loss. In these two as okay cases here, there's going to be a greater loss of energy here and a lesser loss here. Okay. Mainly due to as okay, a greater viscosity is going to cause that okay, yes, it will take more energy to mainly as okay, push this thicker fluid through as okay, this tube here compared to over here. Okay. Where you actually is okay, if you measure the amount of energies at both levels, there's going to be as okay, a lesser difference. So it's okay, here there is a lesser difference between part A and part B, or part A and point B compared to over here, there's going to be as okay, a greater difference in the amount of energies. Mainly because of this fluid here is okay, being thicker. Okay, there was going to be as okay, or having a greater viscosity, there's going to be as okay, a greater viscous loss. Compared to as okay, a case where okay, as the fluid was thinner or had a lower viscosity, there's going to be as okay, a lesser difference between the amount of energy at beginning and at the end due to a lesser viscous loss. Just think of it. Now you have a straw and you drink water through that straw. Okay. Okay. Now, why would it be easier for you to just, okay, suck that water through that straw? Mainly because it is lesser viscous, right? Or thinner. Compared to, yes, okay, if you take, okay, as a thick milkshake, not just milk, which, yes, okay, of course, is thicker than water, but you made it even more thicker by adding, yes, okay, ice cream to it. Okay, okay. A very thick, yes, okay, milkshake. Okay. Now, if you want, just okay, drink the same amount of milkshake through that same straw as you were drinking water, you will have to suck harder on that straw. Mainly because, okay, you will have to overcome some of that viscous loss energy. Okay, that's going to just, okay, cause the milkshake is going to flow at a slower speed through that straw compared to the water. Although it's okay, you apply the same amount of suction pressure. Did that make sense? Did that make any sense?
Yes.
Like you don't want to drink milkshake and water, but rather to, it's okay, push it through the straw. Well, okay, that's the same. You just have to just okay, blow higher. It's okay, harder to blow that milkshake through the straw than compared to water. Did that make sense? Now in blood, what may increase or decrease the viscosity of blood? Or you may say, okay, make blood thicker or thinner. Now, guys, people who are anemic, mainly is okay due to is okay the lower number of cells. The blood may be more liquid because most of the blood is going to be made up of the liquid component, which we call plasma, right? Whereas, okay, on the other hand, what was the opposite of anemia? Somebody was anemic, and the opposite of anemia was yes, guys. This is a question. Lillian may be exempted because she didn't take. But if she can give me the answer, that's more than you're allowed to answer. So what do you think would be the opposite of anemia?
Is it polycythemia?
Polycythemia. What did we say that we had in polycythemia? More cells, right? And due to that, more cells in the blood volume. Yes, okay. The blood is going to become more thick. Or in this case, you can say it's okay, more viscous. Did that make sense? Now just look at that, just okay, in context to just okay, keeping that blood in circulation. That's going to just okay cause an extra workload on the heart. Because now what is it that the heart will have to do? Push with more pressure to push that more viscous blood or thicker blood through the blood vessels to keep it in that speed or motion. Did you guys get that? Okay. So yes, okay, the viscosity of blood, yes, okay, actually is okay, can be measured by what we call, yes, okay, the hematocrit. Where we mainly can say, yes, okay, the greater hematocrit is going to mainly mean that we have a greater viscosity. And vice versa, as okay, a low hematocrit is because of which lead to a lower viscosity. And as my professor used to say, yes, okay, hematocrit should mainly, yes, okay, be 45%. So that's the normal range or the normal value. Okay, where we mainly said that, okay, the remaining 55%, there was plasma. So the hematocrit was mainly, yes, okay, just a test where they check on the percentage of the blood volume made up of blood cells. Primarily, as okay, your red blood cells, because 99.9% of the blood population was red blood cells. Okay, so if that hematocrit meant greater than 45, that will become the blood becoming more viscous, and we will have okay, more will be yes, okay, polycythemia. Whereas okay, on the other hand, it's okay if it went less than that, it will be yes, okay. Patient may be yes, okay, anemic. Okay. Now, guys, please keep in mind that okay, somebody can still have a normal hematocrit and still be anemic. Is that clear? And that's just because the iron contents of the blood is lower than normal. Clear? So that kind of anemia we would what we call an iron deficiency anemia. So viscous loss is mainly loss of energy due to the viscosity, which is the thickness of any fluid. Yeah, okay. So the thicker the fluid, the greater the viscosity, the thinner the fluid, lower the viscosity. Right. And maybe Teresa can show us, how to check on honey next time. Any questions, guys? Nope. Okay. Now the next form of energy loss was frictional energy loss. Okay, where we can make that's okay. Not really loss, but it's okay. I mean, it's okay when we compare the amount of energy that we had at the beginning to the amount of energy that we had at the end. This is always going to be lower and compared to where we started, mainly because some energy was lost as going from point A to point B. So that other kind of loss is going to be friction loss. Mainly because it's that some energy will be lost due to friction. Now, what do we mean by friction? Or when does friction happen? What's going to cause friction? Not fiction. Friction.
When something rubs against something else.
Exactly. Okay. Two surfaces rubbing up against one another. Okay. Now we don't have to go very far. You can make this just use your two hands. Clear. Okay. Now when you rub them up against one another, that creates friction. Clear? Okay. In your blood vessel. Well, okay, yes. If you have a blood vessel. Okay. And it's blood is flowing in this blood vessel here. Of course, that's some of this blood here, especially as this blood here, and the blood that is runs here. Mainly because it runs right up against the vessel wall. Yes, there's going to be a friction between this blood here and the vessel wall. Did that make sense? Clear? Okay. And the outcome of that, guys, is going to be the exact same as you say, yes, this is the vessel wall, and this is the blood. What happens? if I keep on going like this? What's going to be the outcome of that?
Heat.
Heat. So that tell you why it's okay? It's okay. One of the reasons why, as blood is circulating in your body, that it keeps your body warm. Okay, so as I said earlier, it's not actually loss. It is just going to be as okay. Some of that energy that okay is going to be lost, is going to be converted into another form of energy. Here it will just convert into heat, which may have this okay. Keep your body warmed up. Did that make sense? Okay, but what is going to be lost here? Now, since we say it's okay, loss, there's going to be one of the energies which are going to, it's okay, get decreased. Yes, guys. No. Since you guys don't want to ask, then it's going to be me. So this was your blood vessel. There was the blood flowing here. And what remaining, you could say it's okay that between it's okay, this blood here and this blood here, they will rub up against one another here. That's going to be as okay, the greatest friction loss. But loss of what?
Energy.
Okay. Which kind of energy?
Frictional energy.
Nope. The loss is due to friction. So the reason we call it friction loss is because the loss is due to friction. That's why we call it a frictional loss.
So is it kinetic energy?
It's going to be the kinetic energy that will be decreased. And what would that decrease in the kinetic energy lead to?
A slower flow.
Okay, good. A slower flow. Good. And what would that slower flow lead to? Come on, Teresa, you can do this. You're 93% there. There's 7 more percent, and okay, yes, you got your answer. You got a slower flow here, right? Which means that okay, as this flow here will be faster. This flow here will be faster. We can say it's okay. These flows here will be faster. And I just say it's okay that this flow here will be the fastest. What did we call that?
Is it pulsatile?
No. It's not pulsatile.
So then
Anybody?
parabolic? Is it parabolic?
Parabolic. And what did I say yesterday when we talked parabolic flow? I said, okay, that's going to be okay, the common flow that just okay, we will see in arteries. But what tells or what is the reason that okay, yes, it flows faster in the center and okay, slower towards just okay, the vessel wall? Because okay, here, because rubbing up against the vessel wall, that's going to be okay, a greater loss in the kinetic energy due to friction loss, due to loss of friction. Did that make sense? Which may says, okay, this blood here is going to just okay flowing slower, and okay, as we go towards the center, it's going to get faster and faster. Did that make sense? Did that make sense? Now, guys, please, okay, frictional loss is somehow very closely related to viscous loss. Because, okay, you say it's okay, a thicker fluid or more viscous fluid is going to, okay, rub up against with a greater pressure. So in viscous, or okay, the greater the viscosity, the greater will be the frictional loss as well. Clear? And vice versa. So what did we say as okay when the fluid was of a less viscosity? We said okay, roughly said okay, those people could be roughly referred to as being anemic, right? And you wonder why people with anemia most likely say I feel cold. Or I'm cold. Due to lesser frictional loss, due to lesser viscosity. Did that make sense? Now your two hands, yes, okay, you rub them up against or up against one like this. Okay, the faster you move, yes, okay, there's going to be more friction and more heat produced. Well, what can we do to just okay, let's say okay, minimize the friction between our hands, even though we rub them fast. Scooby-Doo, what can we do? Yes, guys. What can you do to minimize the friction when rubbing your hands together?
Take them apart.
Okay, but you still need to rub them. Okay, here.
Go slower.
Okay, you still go this fast. Nothing changing in the speed. What can be done?
If you added like a lubricant, like water, or lotion.
Lubricant. Do you guys drive a car? Why do you want to change engine oil from time to time? Your car doesn't run on engine oil, it runs on gas. But those different things, piston, wheels, and all that, yes, they are in a constant motion, rubbing up against one another, right? Okay, that's going to cause friction, but how is that they reduce that friction? By engine oil. And that's why, yes, if you don't change that on time, yes, okay. What may happen, the next thing you know is your engine may, either crack or boom, go up in flames. So lubrication. So guys, everything we do on a daily basis is physics. We just don't think about it. Hey guys. Any questions? Yep. Now guys, the last loss of energy was inertial loss. Now, do you guys know, or does anybody know what inertia is?
Objects in motion stay in motion. Objects at rest stay at rest.
Right, okay. So pretty much, yes. Let's put it this way, the energy that is required to, to keep an object that was in motion, to keep it in motion. Or an object that was at rest, to keep it at rest. Now, guys, when you, for instance, roll a ball on the floor, clear? You want to play fetch with your four-leg fellow. Okay? Whether he or whether that four-leg furry fellow catches the ball or not, that's not the question here. But what you will see is that ultimately, at some point, that ball comes to rest. It goes from motion and stops. Clear? Okay. Where, what had needed to be keeping it in rest was going to be further energy. So main is prevented from slowing down and go from motion to a complete stop or vice versa. Okay. That energy that's going to be used to keep an object in motion once it is in motion, is going to be as okay inertia loss. Now, have you guys ever wondered that, for instance, okay, if you are sitting in your car, oh, I could probably do that better. It's okay, you are sitting in your car, driving at, okay, yes, at crazy speed. But then all of a sudden, yes, okay, apply a brake. Have you ever wondered why is it that, okay, yes, this part of your body here may go like this? Okay, what's going to prevent you from going like this is mainly as okay, hopefully it's okay that your whole is okay, having a seatbelt on. But if not, just okay, you were gone like this, and okay, yes. Now, guys, that's mainly because okay, your lower part of the body is okay, as the brakes are applied, is okay. That comes to rest. Well, okay, this part of your body still is in motion. Or still isn't going to be as okay in a state of inertia. And that remaining me as okay, still be moving. And that's why you go like this. Did that make sense? Yeah, okay. Likewise, okay, if you, for instance, okay, were standing up somewhere. And that vehicle, train, bus, whatsoever, is okay, all of a sudden, yes, okay, starts moving. Why is it that you, yes, okay, if you don't hold yourself tight onto something, you may fall? That's because now here's okay, this part of your body here is okay, is in motion, but this was still in rest. So this still being in rest is meaning going that it was still is okay in inertia. Did that make sense?
Yes.
Right, okay. Now, the main thing that's going to be important here that, okay, yes, there's going to be as, okay, inertial losses of energy at 3 stages in the blood vessel. In pulsatile flow, clear. And where do we see that? We saw that in the arteries. If we as okay come across that okay as phasic flow, which we saw as okay in veins. Now this was controlled by as okay contraction of the heart. This was just okay controlled by the respiration. But these two are not going to be as okay the important ones that we will talk about, but rather what we is okay we say is okay will be as okay the velocity changes at a stenosis. And let's say okay off a blood vessel. Because that was pretty much okay what happened here. The velocity change here from, let's say, it's okay, 100 miles per hour to 0 miles. Or in this case, it's okay, from 0 miles to 100 miles per hour. In no time. So that was changes in the velocities. And we're going to just, okay, have similar changes in velocities at the stenosis of a blood vessel. Now, what we already said is, okay, where's the common blood vessels? That's okay, where we see stenoses or narrowing. Prime, that's okay, still is arteries. Okay. But mainly that's okay, just to still, that's okay, overcome some of those changes in the velocity is going to cause there will be, yes, okay, some loss of energy, which is going to be, yes, okay, what we call inertial loss. Okay. Now earlier, yes, okay, Teresa said an object in motion is going to stay in motion. The object at rest is going to be at rest. That's the first law of motion given by Sir Isaac, what was his name? Isaac Newton, sorry. Okay. That law mainly as okay also explained inertia. Clear? Okay. And mainly as okay also as okay explained as okay gravity. So it's okay, that first law of motion mainly as okay laid the foundation to yes, okay, explaining gravity and enabling us, okay, somebody to calculate that value, which was 9.8 meters per second square. Being as okay, the pull of gravity. Any questions? Nope. Okay, guys. Now, what I would recommend you guys doing is read on your energy losses, and in the meantime, I'll be sending you guys a little email with 2 pictures. Now we're just going to reproduce those 2 pictures or drawings. But yes, okay. We can mainly say, okay, the reason that we have done the talk so far was mainly as okay to build up some okay ideas, some concepts to be able to okay understand the info that we'll come across now. Okay. So yes, okay, read on your energy loss. Read on yes, okay, your energy gradient as well. Look at your flows, turbulence, and pulsatile or laminar, and so on. So, because okay, when we come back, we will talk about it's okay an important topic, which is going to be okay stenosis. Okay. So, okay, I need your lunch too. So I see you guys, should we say around 12:20ish? And it's going to be a long hold. Now let us just try to just okay reproduce it all and talk about it. Okay. And so we can mainly say that okay, yes. The main thing that we will be talking about is going to be stenosis. Okay. What stenosis mainly is okay just means is narrowing of the lumen of we can say it's okay tubular or passage. Okay. So we can say it's okay if we for instance okay had a blood vessel. If that blood vessel is okay at any point is narrowed down. Okay, and as you can see, this is not going to be something that normally will occur. Okay, R is narrowed down. Most likely it's okay due to plaques. Okay, that's the common reason. Okay. But it may also be that okay, yes, in some instances, okay, the blood vessel actually is okay, also can be narrowed down or stenosed, if that's what you want to call it, due to a structure right next to it that may grow to an extent that it actually is okay, pushes up against the blood vessel and cause it to narrow down. Okay, but with that said, it's okay. The common reason for narrowing of blood vessel is most likely going to be plaques or atherosclerotic plaques or fatty plaques. Is that clear?
Yeah.
Good. Okay. So, but right now, yes, okay, our main point is okay, point of interest is going to be okay, how is it that this stenosis here is going to, yes, okay, affect things such as the flow, the pressure, things such as, okay, as velocity of the blood as it flows through this blood vessel here. Okay, so to do that, let's just check a blood vessel. Now this is the blood vessel, right?
Yeah.
Okay. No, I just see two lines. That's plain. It's a blood vessel. Okay, good. Okay. And just to get it straight, you mainly say, okay, that the blood in this blood vessel that we were talking about here is okay, is going to be flowing. Let's say it's okay in this direction here. Okay, so you can mainly say, okay, that the blood is going to just, okay, start here, and mainly it's okay, just flow in this direction to begin with. Okay. Now, in that, yes, okay, let's just make our plaque. We can say, okay, arteriosclerotic plaque. Okay, so what can we do with this point here? Okay, now we can just label it as E. But what is it that it will be? This will be as okay, or we can call it as okay, the pre-stenotic. Because as far okay, the flow of the blood is concerned, it comes before the stenosis. Clear? Okay, so it comes before the stenosis. That's why we'll call it pre-stenotic. Okay, but please, 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 guys, keep in mind that okay, as this area here may also be referred to as upstream. Okay, so that's a term that okay, as they may use, referring to as okay, a pre-stenotic area is okay when asking about the things that we are going to discuss here. Okay, now the area is okay where we have the stenosis. Well, that's going to be stenotic. Yeah, okay, which made us okay, just make this area over here. Okay, which means okay, that's okay, we see. So it's okay, this would be B. Okay, and C is okay, is going to be post-stenotic. Right, because it's okay, it comes after the stenosis. Or as it also may be referred to as downstream. Did you guys get that?
Yep.
Good. Now, guys, as far as the flow patterns are concerned, will be pulsatile. Here is it that we will have a turbulent flow. Okay. Initially, it's okay. after the stenosis as well, that's okay. Will also be turbulent. But then it goes from turbulent to get steady. And just to make it okay. After which, yes, okay, it will regain back to become pulsatile. Okay. But right, yes, okay, right at the stenosis. That's where, yes, okay, we will see a turbulent flow. Okay, right, okay, yes. Right immediately after the stenosis, yes, okay, still turbulent, but then becomes steady. Now, what did we say that steady was? There was no changes in the flow. Constant or smooth. Okay. So initially it's okay, maybe because it's okay, we talk about it's okay, there's being an artery. So it's going to start off as being pulsatile. It would have kept on being pulsatile had it not been for this mess that came up here. Did you guys get that? So at a stenosis or at a narrowing, that's okay. You will see turbulence. Followed by it's okay, a steady flow, and sooner or later it's okay, it's going to become pulsatile again. Did you guys get that?
Yep.
Good. Now, the next thing that we will be looking at here, guys, is going to be our pressures. Our pressure. Pressure. And pressure. Okay. Now, in the area, yes, okay, where we have, it's okay, where there's going to be the pulsatile flow, that's mean that's okay, where we can say, okay, that we will have the highest pressure. At the stenosis will be, yes, okay, the lowest pressure. Whereas post-stenotically is going to be, yes, okay, a low pressure. Clear, okay. So, yes, okay. Upstream, or yes, okay, pre-stenotically, yes, okay, where we have the pulsatile fire, that's going to be, yes, okay, where we have the greatest pressure. At the stenosis, yes, okay, the lowest pressure. And post-stenotically, yes, okay, a pressure which is going to be, yes, okay, lower than what we had pre-stenotically, but still not as low as what we had at the stenosis. Did you guys get that?
Yes.
And when we say pressure here, it's okay, what is it we actually are talking about? Is actually, it's okay, the pressure energy. Now the next energy is okay factor that we maybe talk about is going to be our, we can say it's okay, kinetic energy. But what I said was that okay, as kinetic energy, that is going to mean is okay, translate into velocity. Okay, that's going to translate into velocity. Now, guys, it may sound crazy, but it's okay here. It's going to be it's okay to lose velocity, or we can say it's okay to lose kinetic energy, which mainly is okay at greatest velocity at the stenosis. And here, well, okay, yes, we will have a greater velocity. We have a greater velocity. A velocity that's going to be greater than what we had pre-stenotically, but not as high as what we had at the stenosis. Did you guys get that? Okay. And how do we get that? How is that? That's mainly as okay because when we said pressure energy plus kinetic energy. Clear, okay? It's okay, add up to is okay what we call the total energy. Which we said, okay, was going to remain constant at all points, whether that was E, whether that was B, or whether that was what we call C. So when we add the pressure energy and the kinetic energy at this point here, point E, which is pre-stenotic, it got to be equal to just, okay, the sum of the two energies if we added at the point of the stenosis and at the point of, yes, okay, post-stenotic. Clear? Okay. Did you guys get that? Now, practically, yes, okay, this was what we, yes, okay, previously, yes, okay, could have referred to as being the law of conservation of energy. By us, okay, studying the law of conservation of energy, by us, okay, looking at pressure energies and kinetic energies. Mainly, yes, okay, was going to be, yes, okay, what we'll call the Bernoulli's principle. Did you guys get that?
Yes.
Yeah, okay. So what this dude Bernoulli's did, he mainly, yes, okay, studied the relationship between pressure and kinetic energy. Okay, what we just can say is that, okay, as this pressure energy here is going to lead to, yes, okay, we can say, okay, pressure. But okay, this kinetic energy here mainly is okay, just going to be released, okay, translated into velocity or speed. Okay, but the sum of these two at any point, A, B, or C, is always going to be the same. Did you guys get that? Okay, so the Bernoulli's principle mainly is okay, was just the sum, is okay, starting off pressure plus kinetic energy. Oops, no, that's not what I meant to do. Here we go. Okay. Is there any questions?
No?
Okay, guys. Now, do you mind if I go to another slide?
No.
So we can just, okay, still make our blood vessel. You can still see that, okay, yes. This was where we had the stenosis, we call that B. We say it's okay, pre-stenotic. It's E. And okay, yes. Post-stenotic was C. Now, guys, another relationship that we may be referring to is going to be as the, what we can call pressure flow relationship. Okay. Now, what did we say that we had at the, here we had the greatest pressure. Here we say it's okay that we had the lowest pressure. And here it's okay that we have a pressure that was great, but it was lesser than what we had pre-stenotically. Okay. So now, based on all this, that's okay. What are we going to say? Okay, it's going to, yes, okay. We will talk a bit about, yes, okay, what they call the pressure flow relationship. Okay. Now, if you look at your book, they, yes, okay, talks about something which is just okay, the Ohm's law. Okay. Now, I don't really know what why they put the Ohm's law there. Okay. But what Ohm's law is mainly as okay, the same pressure to flow relationship, but when talking about electricity. Clear? Okay, so you can make this okay, just omit that one. Okay. Here we are not talking about as okay, the flow of electricity. We talk about as okay, the flow of a liquid. But what is okay, the pressure flow relationship or fluids in terms of electricity is okay, that same law was called Ohm's law. Did you guys get that? Okay, so what is it that your pressure through flow relationship is going to be? Now that's mainly going to be as okay, what they will say as okay. Or what they say is that your pressure gradient. Okay, now all of this pressure gradient here, that I mean that's okay because it's okay, just the difference of pressure between 2 points. Where we say it's okay, A to B, B to C, or A to C, even that was going to be as okay. The difference in those pressure, that was going to be as okay, what we refer to as the pressure gradient. Okay, but what we actually as okay have to do is, okay, yes, we have just okay establish a relationship of this pressure or the pressure gradient to flow. Yeah, okay. Now this pressure gradient and its relationship to flow is going to be that, okay, yes, the pressure gradient is going to be equal to the product of flow and resistance. Okay. Now, what this relationship here is mainly going to, or mainly it says is, okay, that's if this pressure gradient here is okay, when we keep that constant, if this value here, pressure gradient, if that is constant, that will mainly mean that you will have a greater flow if you have a lower resistance. And or vice versa. You have a lower flow if you had a greater resistance. Yeah, because the product of these two things here, flow and resistance, has to produce a constant value, which we say is okay, will be your pressure gradient. So if one increases, you can't multiply with a great number as well. And it's okay, expect to get the same value here. As you did if you says, okay, well, I decrease the flow and I also decrease the resistance. So flow and resistance are going to be as okay inversely proportional to one another. Greater flow because of lesser resistance. Lesser flow mainly is okay due to a greater resistance. Did that make sense?
Yes.
Good. Okay. Now, one thing that you also then can see is that, okay, yes, whether it is the resistance that increases, or the flow that increases. Both of these, that's okay, well, that's okay, lead to, that's okay, a greater pressure gradient, which mean a greater difference between the pressure between 2 points, point A or B, A or B or C, or A or C, whatever. Whereas, okay, as if we decrease the flow, or if we decrease the resistance. The reason I say or, okay, that will cause that the pressure gradient will decrease. Okay, but you can't increase both flow and resistance. When you increase the flow, that's because you have a lesser resistance. Or when you okay, increase the resistance, that's going to give you lesser flow. Or if you reduce the resistance, that's okay, you will have a greater flow. And what was flow? What was flow? What was the earning for flow?
Was it motion?
Okay, motion or what? That's when we use the word flow. That was motion of what?
Fluid,
Fluid or
Blood?
okay. Or
Gases?
gases. Guys, wake up. Yeah, okay. Well, okay, as when there was solids, just okay, that was going to be as okay motion. That's when we use the word motion or movement for that. Okay. In electricity, yes, okay, that flow of electricity is not called flow of electricity, that's called conduction. Have you guys ever heard of that? What will happen if you, yes, okay, hold on, yes, okay, to a good term conductor and touch an electrical field?
you get shocked.
You get shocked because that conductor is made as okay, going to cause electricity to flow from here to you. What is a good conductor?
Water,
Okay. Something that people like to wear.
watches, jewelry, rings.
Jewelry, here you go. Okay, gold is a good conductor. That's why it's okay if you open up now. Don't do that. You're probably not going to get enough gold to it's okay make a pair of earrings. Okay, okay. But why do they ask you to yes, okay, not throw our electric devices and so on? So because they have good conductors which can be reused. I don't know, but it's okay. Gold. Okay. Now don't go for your okay electrical wires because they don't carry gold. What do they use in electrical wires? That'll be a question for
You use
Kristen.
a casing. It's a rubber casing that
Okay.
goes over wires.
Okay, but what do they? Yeah, that's going to be an insulator, right? But what is it that the wires are used, or what do they use as a conductor in the wires?
Is it copper?
Copper. Okay. Have you guys read about the different ages? Stone ages and things like that. I've never heard of those things. So there actually is was an age of bronze. Okay, where most of the utensils, yeah, they didn't have electricity back then, but it's most of the utensils, pots, etc., was made out of copper and then bronze and things like that. Okay, peace be with that. Okay. So that's either increasing the flow or decreasing in the resistance. Okay. Will lead to, a decrease in the pressure gradient. But what we know is if we reduce the flow, there's going to be an increase in, it's going to be due to an increase in the resistance. Or that if we increase the flow, mainly it's going to be due to a decrease in the resistance. Yeah, okay. Did you guys get that? But the product of these two here is going to determine the pressure gradient, which is going to which was the difference of pressure from point to point to point to point. But what we mainly said to establish this relationship here that we want to keep this pressure gradient here constant. So where is the difference between the pressure of A to B, B to C? We want to keep that constant. Did you guys get that?
Yep.
Yes. Any questions so far? Yes, guys.
No.
Okay. Now, one thing which, you won't find in your book. Clear, okay? One thing that you won't find in your book, but which is as going to be as important, as we can say helpful to understand the relationship between prime level velocity and the blood flow. And the area of the blood vessel. So that's if you that okay. So we will find that on our second slide. And we mainly can say it's now we had our blood vessel. Okay, we said as the blood was flowing in this direction here. Okay, at whatever speed. Okay, we said as here we had a stenosis. Okay, now we call this area here stenotic. We call this area here stenotic. And what we had after the stenosis was going to be as post Stenotic. Did you guys get that? Okay. Now what we already said was that as far as as our velocities are concerned, yeah, okay. Now this was the area, where we said that we had the lowest velocity. As we said, here this was where we had the highest velocity. And here we had a high velocity, but not as high as here. Or we can say, we had a low velocity, but that velocity was not going to be as low as we had here. Okay. Now the reason that I do that is mainly just to say, wherever you have the greatest, lowest velocity, that's going to be where you have the greatest pressure. So here we had the lowest pressure. And here's we have a pressure, which was low, but not as low as what we had at the stenosis. But the thing that you don't have in your book is mainly an equation that we call that they call the continuity equation. Okay. Which mainly is going to we can say establish the relationship between flow to the area and velocity. So the continuity equation here mainly say that as flow is going to be equal to the product of what we may say velocity times area. Is that clear? And guys, what we mainly say about the flow here as well in this equation is that remains constant, which mainly means that so if we keep the flow constant, which is the volume or the amount of blood that flows through a certain area, if that remains constant, and that constant value of flow is going to be equal to the product of velocity and speed. And area. That mainly means that yes, an increase in either of these two here will mainly mean that yes, you had a greater flow. Or as you can say as a decrease in either of these will have led to a decrease in flow. But mainly as because the flow is kept constant. What we mainly will say is that yes, velocity has to be inversely proportional to the area. which mainly or mean that, okay, yes, if the velocity is increased, that's because we have a great area. Or if the velocity is greater, that's because we have a smaller area. Now, what do we mean by the area here? What when we say it's okay, areas, okay, what is that we are referring to? Mainly it's okay, the diameter of your blood vessel. Because we say, okay, here we just look at the blood vessel, but it's okay. If you take it in a cross section and say, well, okay, here, this is the area. Well, okay, the blood vessel is still this big over here, but here's okay, the area of the lumen is narrowed down because of the, you can say it's okay, this stenotic plaque. So this is what's remaining of your lumen. You can say it's okay, yeah, this is what's remaining of your lumen. Did you guys get that? So mainly because of, yes, okay, at the stenosis, what do we have? We have a smaller area. Or it's okay, the smallest area of the passage. Which mainly will mean that that's going to be as okay where the velocity is okay will be at its greatest. Did you guys get that? Okay. Now you can say it's okay, the reason that okay is you have a velocity which is greater here compared to yes, okay, what it was over here. Although it's okay, the lumen may be the same, you can say it's okay, that's because it's okay. The velocity is okay, is post-stenotically is still going to yes, okay, be influenced by the great velocity. Or that's okay, that's an increase of the velocity at the stenosis. Okay. Did you guys get that?
Yeah.
Okay. Now what do you, okay. So what does this whole thing here so okay mean that we say, let's just look at our highway. We say, okay, we want the flow at this area here to be equal to the flow at this area here, although it's okay, this is going to be it's okay where the road may be shut down due to construction. And of course, it's okay, we also want it to be equal here. Okay. Now, what will we mean by the flow? To be constant. That's okay, same here, to same here, to same here. What would that mean? That the amount, how much? Clear, okay, now when we say how much, that's because, okay, we really can't count. We can just measure it, and okay, as the volume. But let's just say it's okay that this was okay as a road where you mainly say, well, okay, yes, in a distance of a mile or half a mile, that's okay. The flow of cars is that there's okay, yes, 1,000 cars flow per minute. Did that make sense?
Yep.
Right? Now, yes, okay, we had, let's say, it's okay, 10 lines or 10 lanes, for instance. So it's okay, 10 cars will flow in each line or each lane per minute. Here it's okay, I do to it's okay, a construction, probably not. Let's say it's okay, an accident. But maybe it's okay to prevent a traffic jam from occurring or buildup of traffic. We says, okay, we still need just okay have the same flow through this area here. All this okay, we are from this okay, 10 lanes just down to let's say it's okay, 2 lanes. That will probably mean that okay, yes, if you still need to have okay, yes, 1,000 cars just okay flow through this area here per minute, they gotta speed up, right? Did that make sense?
Yes.
Yep.
That's how you can explain it. Okay. So mainly it's okay, just understand it's okay, remember this relationship first, and then it's okay related to the pressure. Because when what we said is okay, in accordance to it's okay Bernoulli's principle, that the sum of this or the product of this is going to be equal to the sum or product of this is going to be equal to the sum or product of this. Any questions?
No.
Good. So if I was you, what would I do? Nobody will know what I would do if I was you. Now those 2 pictures that I sent you, yes, okay. Either draw them yourself, write it down, or put it up somewhere that you look at it day in and day out. Okay, guys? Now, just another thing. And what we actually, that's okay, we'll be seeing at, and that's mainly it's okay, the point. Or we will be seeing at, let's say it's okay, stenosis. Mainly it's okay due to the, because it's okay, very high velocity. Right, okay. Due to the very high velocity. What we actually is okay, we'll see in Doppler. Okay. And not just any Doppler, but it's okay, which is okay, pulsed wave Doppler. At this stenosis here, it's okay, we are going as okay. So okay, we had the turbulence, but not really due to the turbulence, but actually it's okay, it's due to the high velocity. In a pulse wave Doppler, that is going to is okay, lead to is okay, something that we will call aliasing.
Can you spell that?
Aliasing
Yep. Can you spell it?
is written right here.
Yeah, I know it's written right there. I can't read what it says.
It's ALIASING.
Thank you.
Do you know what this is?
Yes, I know what an alias is, but I didn't know
Oh.
what that was spelling. Thank you.
So do you mind tell us what an alias is?
It's like another identity.
Okay. And that other identity, would that be real or not real?
Not real.
So you are, yes, okay, that's your underworld identity, right? Or you try to pose as somebody who you ain't by using an alias, right? That's fine, guys. Okay, this aliasing, that is one of the major topics of your Doppler. So where will you see that? Most likely at a stenosis. Why? Primarily, that's okay, due to the high velocities. But only when using, yes, okay, what we call a pulsed wave Doppler. Yes, guys. Any questions? Yes.
Do we have to know the Poiseuille's law?
Poiseuille's law is just what they call the pressure flow relationship. So Poiseuille's law is mainly as okay, just studying that. Okay, for fluids. Did that make sense?
Yeah, I guess.
Okay, okay. So what Ohm's law talks about when talking about is okay, flow and resistance. In terms of electricity, Poiseuille's law is just the same relationship of fluids flow and okay, yes, it's pressure or resistance. But not, you don't necessarily have to remember the names of them. Okay. But the relationships, yes, the relationships are important. Okay. But with me, it's okay, just two laws if you want to put it that way. Yes, okay, you have the Bernoulli's law, which was meaning it's okay, just your another name for is okay, law of conservation of energy, talking about the relationship between pressure and kinetic energies. Clear? Okay. Poiseuille's law, yes, okay. That's what we call as okay, pressure flow relationship. Or we can mean that's okay that Porcelli's law is okay, mainly is okay, just explain the flow, pressure flow relationship. But you don't need to know about Ohm's law. Okay, I don't know why in the blue they put that there. Good. So guys, pretty much okay as what we had talked about for the last 1.5 days. Primarily as okay was just to build up to as okay what we just did. Talk about as okay, where is flow, what's velocity, what's this, what's that, what are the energies, so and so, etc., etc. All that was mainly is okay just to build up the concept of okay, that's what we just talked about. Now this here is okay, may need some reading. So that's what I would do if I was you. Okay. Bless you guys.
Thanks.
Any questions, guys? I'm not going to be bombarding you with more. Bull crap yet. Nope. Good. So you have some homework to do over the weekend. Okay. And guys, please, 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 if you haven't done it yet, it's about time to start your revision. Okay. In 4 weeks from now is going to be as okay the day when you will finally hand over your final tests. Okay. So. And yes, okay, the material is volatile. So yes, okay, you may tend to forget what the relationships of okay as an older chapter was. Okay. Should I put some pressure and ask you to increase the velocity too of answering? You guys are not in a Jeopardy mood right now. How does depth affect your pulse repetition period? Depth of image, okay, sorry. That's directly related, guys. You forgot that? Then there's a chapter 4 and 7 that needs to be read. Good. In your PRP, if you needed to change your on time, what would you change? Or would you change that? How will you change your on time in the pulse repetition period?
Increase the number of cycles.
Okay. They're running low on cycles at Walmart right now, so how do you just increase the number of cycles? I don't know. Yes, Dr. Lillian. Do we have a knob where we can turn or twist it and it will increase the number of cycles?
I'm guessing yes, but I'm forgetting what.
No, we don't, my dear. Right? I don't think I've shown you something that okay, as is going to is okay that you could twist and it is going to is okay increase the number of cycles. You can only as okay do so by as okay using or changing a different transducer. In your PRP, the only thing that we could change on the system was the off time. Yeah, okay, where P is okay, whereas the pulse duration remains constant because both of those were determined by the transducer. The period of each cycle was determined by the transducer. Clear, okay? And the number of cycles was also is okay determined by the transducer. It says okay, the more backing material, that's okay, less the number of cycles because there's more damping. Okay. So the only thing that you can do to is okay increase or is okay change the pulse duration of your pulse repetition period was by changing the transducer itself. That's why it says okay, that value remains constant for a specific transducer. So the only thing in your PRP that you change is the off time. And how do you change that? How do we change the off time in a pulse repetition period?
The increasing the depth.
Changing the depth, right? Okay, clear? Okay, increasing the depth will increase the off time. Decreasing the depth will decrease the off time. That makes sense? Okay, so that off time will mean is okay, just your go and return time or listening time, the time that it takes the pulse to go to the depth and return back. Did that make sense? Good. What's going to be the speed of sound in soft tissue if we change the frequency from 3 megahertz to 6 megahertz of the transducer? What's going to be the speed of sound in soft tissue if we increase the frequency of the transducer from 3 megahertz to 6 megahertz?
Gonna be no change.
How many?
Be no change. Be 1.5.
There's no change, right? Why? Why won't it change?
It's only dependent on the medium.
And I said, well, okay, that's soft tissue, right? Okay. 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 What will change? Now, since speed doesn't change, but what will change if we change the frequency?
Wavelength.
The wavelength. Yeah, okay. Now, which transducer will have the best exit resolution? One with more ringing or less ringing? We have two transducers. One is having more ringing, one is having less ringing. Which of these two here will have the best exit resolution? What do we mean by less ringing? Anybody? Did that ring a bell?
Fewer pulses. Or fewer cycles.
Pure cycle, right? Okay. So fewer cycle, smaller pulse. Smaller pulse, lower numerical value of your exit resolution. Lower the numerical value of any of your three spatial resolutions, axial, lateral, or elevational, better resolution. Or we can say, okay, more likely to give you a better resolution. Yes, guys. How is the diameter of the PCT related to the beam divergence?
Inversely.
Inversely related. Good. Okay. How does the line density affect your spatial resolution?
More line density would improve your spatial resolution.
So you can say it directly, right? Okay. Okay. More and more. Okay. Increase, increase. Okay. How is mechanical index related to the frequency?
Isn't it a lower frequency, a higher mechanical index?
So what do we call it? One is higher and one is lower?
Inversely?
Inversely. Okay. Now, at what frequency range is the size of the microbubble be equal to that of a red blood cell? At what range of frequency is the size of a microbubble going to be the same as that of a red blood cell.
2 to 4 megahertz.
2 to 4 megahertz, exactly. Okay. That was written. And it says, okay, a nice coincidence or something like that. Okay, so that's a number that you guys is okay will have to remember. Okay. What will happen if the frequency is okay is decreased? What will happen to your microbubble then?
It wouldn't expand as much.
Or it will expand. It will expand too much. Because you're going to just, okay, increase the mechanical index. Clear, okay. That may causes, okay, overexpansion of the microbubble, and when something is, okay, expands beyond its ability to expand, what will happen? You have a balloon, it can only hold so much air, but you pump in so much air into it. What's going to happen?
It'll explode. Burst.
Okay, let's not, it will burst. Okay, go into explosions. Okay. Okay. Now, as a result of more compression, what is going to happen to the dynamic range? The more a signal is compressed, what's going to happen to its dynamic range?
It reduces.
It reduces. Now, as your dynamic range reduces, what will happen to your grayscale?
It will also reduce.
It also reduces. Good. What do you call the case or scenario where we have the smallest grayscale? Smallest grayscale is known as what?
Bistable.
Hmm?
Bistable.
Bistable, exactly. Okay. How many bits make a bistable grayscale? How many bits would we need?
One.
Huh?
One.
One. Uno. What if we needed 3 shades? How many bits would we need then? If we have black, white, and 1 gray, how many bits would that take up?
2.
2. Good. What about 4 shades? How many bits for that?
2.
Still 2. From 5 on to 8, it would be 3. And then you go on like that, okay? Yeah. Good. Okay, guys, I'm not going to be bugging you guys anymore. Take a rest. I'll see you guys on Monday, okay? And okay. It looks like, okay, as we're going to be off with this chapter sooner than I thought. I had expected some more questions regarding the flows, regarding the velocities, regarding the energies. But, okay. Please be with that. If you come up with something, please feel free to ask, okay? Because